Yeah, I'm very happy to introduce Kumar Sridhar, who is a final year PhD student at ETH Zurich. Um, he's been working on pretty exciting topics during his PhD, topics that we care about a lot, like reasoning, alignment, safety, agents, and so on. Um, and today he's talking about enhancing reasoning in smaller models, also something that we find pretty exciting here. So go ahead, Kumar.
Thank you. Thank you so much, Pradeep. So as I have already been introduced, so I'm Kumar Sridhar, doing my PhD at ETH Zurich. Before I start, please feel free to ask questions anytime you want. So I'm happy to stop and answer those questions. Also can keep it interactive. I'm going to talk about enhancing reasoning in smaller models through self-training. And we'll go through all the keywords which I have mentioned here in details. But before I go there, a quick things about myself. So doing my PhD at ETH Zurich, I'm supervised by Mrinmaya at ETH and also Nicholas from DeepMind. And I work on reasoning or improving reasoning in smaller models, and that usually goes around distillation, a bit of verification or refinement. And now I have been working on multi-agents. So this is a picture I took from small LM2, which also feels like a distant past. But this image is basically saying that smaller models are getting better every day. And if we take this figure and compare this with some models which were like 2 years ago, I hope you can also see my cursor. So if we compare this with models like GPT-2, which were like maybe 3 years ago, something like that. So as we can see the model size is going up, we also see the performance is going up. So y-axis is win rate, meaning how good the models are in some way, and on the x-axis we have the model size. And if you compare this with the small LM models now, so these are kind of similar size, so in terms of model parameters. And if you see the performance is really like exponentially better than all the models from the past. And this has to do with a lot of things. So our entire pipeline has improved over years. So we have better data sets now. We can pre-process the data better. We have different kinds of pre-training strategies that we are using. And then once the model is pre-trained, we are post-training it with a lot of optimization techniques, so including preference optimization, some kind of online, offline training. And then we also have knowledge distillation that is being used lately a lot. So in my talk, I'm mostly going to talk about two of these post-training strategies that we have used in our work, and mostly around how we can leverage knowledge distillation from a large model and put this into a smaller model, and how you can design your online or offline training strategies with that. And this entire thing of distillation is important. And we have seen just about yesterday that DeepSeek R1 came out. And then this R1 was very impressive on like a lot of different things. But one of the very impressive results was you can generate a lot of data from this DeepSeek R1 model, which is like some thinking style models. And then you can distill all these reasoning capabilities into smaller models. And then if you check this model, this is Qwen 1.5 billion model. And this is like comparable to GPT-4 or Claude 3.5 Sonnet, like 6 months old or so. And this is like on very competitive mathematical examination or math dataset, which is kind of challenging in my opinion. And a model as small as 1.5 billion can give us like really good performance. So a lot of distillation has been used here. So before we go into distillation, like let's just look into what exactly is knowledge distillation. So in short, it's like a process of transferring knowledge from a large model to a smaller model. So in other words, if we see, for example, for a reasoning task, so we have two steps. So the first one is a generation step. So we take a problem, we feed it to a language model, a large language model in this case. And then we generate some form of reasoning chain. And the reasoning chain could be of like any type, but in this case, we are, let's say, using some form of intermediate representation. And then the model is generating our reasoning chain and eventually the final answer. And then with this knowledge distillation doing this knowledge distillation into a smaller model, we take our same problem and then we have this reasoning chain which is generated by this LLM. We combine this problem and reasoning chain, and then we feed this to a smaller model and we train the model. And then since everything is an autoregressive model, so we just append this problem and reasoning chain to some form of fine tuning or some training. And this is how we distill this knowledge into a smaller model. So we did this early 22, late 21. At that time, GSM-8K came out, so it was a very new data set. GPT-2 was there, and GPT-3 came out like around that time. So I'm talking about like just GPT-3 based models, so no instruction tuning, nothing. So we were generating all kinds of data from GPT-3 model, and then we were training this GPT-2. We were distilling this into GPT-2. And if you see this gray bar, so this is higher than this green bar, which was our base model, so which was non-distilled. And then blue one is the accuracy from, so y-axis is the accuracy, and then blue bar is the accuracy from the teacher model. So at that time, teachers were not that accurate, so around 45% was what we get. But then the interesting thing is, even though there was some improvement with distillation, there was a huge gap between the teacher and the student model. And ideally, in a very good distillation setting, this gap should be as low as possible. So then the obvious question is, what can we do to reduce this gap? So there could be two scenarios here. So there could be the limitation of the smaller model. So smaller model might not be capable of learning some complex reasoning tasks. And GSM-8K was fairly challenging for GPT-2 models because we are talking about models which would just produce the same text over and over again. They were not trained enough, so they were not capable of learning. And probably in pre-training data, there was very little mathematical data sets or coding data set that was there. So it might be due to the limited capabilities of small models, or it could also be that there is a distributional mismatch between the large language model from which we are generating the data and then the small language model, what it is learning. So this can also be verified in some ways, but we can also say that there could be a distribution mismatch, and that's why we are not getting the performance that we want. So starting with the first problem, so if there is a limitation of the small model. Also, one thing, I am not seeing the screen, so I don't know if you are raising your hand or something, so please feel free to stop me whenever you want. So how do we solve the limitation of the smaller model? So one very obvious naive solution is scaling. And this we have seen time to time that this seems to work. So you can scale both models here. So the teacher performance was also not very good. So basically, in some reason, we were limiting ourselves with a low performance teacher. And then obviously you can also scale the student. So this is what we exactly did. So on the left side, this is the same plot that I was showing you. Now, if you see, you can directly see that if you scale the student, so this orange plot, if you scale GPT-2 to GEMMA 2 billion and further to GEMMA 7 billion, you can see there is like the scaling law into effect. And also if you scale the teacher, so you can also have a better teacher. So from 40%, you can also have teacher that goes like 90% or something. So it obviously shows that if you change the teacher and student model, so you can get better performance with both of them. And the more you scale the student, the closer it is getting to the teacher model. So this is something which we want. But this is just one side of scaling. You can also scale the data set. So this basically means that we were using like GSM-8K data set, which was very small, like approximately 8,000 samples. Each sample was a couple of hundreds or maybe early thousand tokens. So how about you scale this data set to a similar data set called MetaMath? So MetaMath is just an augmented version of this GSM-8K data set where every problem has been rewritten in different styles. And so the model has more samples from which it can learn from. So on this same model and same teacher combination, I'm showing just the student. So Gemma 2 billion, when it was trained on GSM-8K dataset, so fewer data points to Gemma to MetaMath, so same model's performance went up. And this also seems quite like easily understandable because this is what we are also seeing with the current models nowadays. So this also falls into the same scaling laws that we were talking about. But then there is also a third side to it. So how about instead of changing the models or the data sets, you can also change the reasoning strategy which was used to learn this. So what I am trying to say is chain of thought might be difficult for some smaller models for some specific tasks to learn. So how about you put some decomposition there and you break your task into some smaller tasks and then you try to solve them iterate. But let's say my task is finding n numbers in a Fibonacci series. So for that specific case, it would be beneficial for me to learn a program rather than solving a task directly. So it kind of makes sense to also think about from this perspective that if we are training a model, it might also be important to give it right reasoning strategy to solve a given task. So I am quickly showing, we all know about all these reasoning strategies. Just to show this quickly, chain of thought is basically saying instead of directly answering a given problem, you can go and write all the intermediate steps, and this intermediate steps would help the model in solving a given task. The decomposition, one of the examples is least to most. So it is saying instead of directly solving a given task, you break it down into some intermediate sub-question. Then the model can solve that sub-question. Condition on this. So you generate first sub-question, condition on this, like you try to solve it. You take the question and your sub-question and your answer here and generate the next sub-question, then the model can solve it. And this is an iterative process. So kind of decompositioning your problem into simpler problems, solving it and so on. And obviously program of thought is just saying the same thing instead of chain of thought style. So instead of free form English or any language style tokens, you can write a program which can then be executed to get to the answer. So for example, this Fibonacci series, it would be beneficial to write a program there. So this is just another way of saying more structured generation so that it can be executed and you can get the answer back. So then we try to train the same student models on different kinds of strategies. So here I'm just comparing 3 strategies that we took, and then we are just training on the same GSM-8K data set. We asked the large language model to generate data in these specific strategy forms. And then we are fine tuning these smaller models on the generated data from the large language model. And this is the output. This is the result that we got. And in some way, we are saying that for some tasks, maybe structured program might be better. For some tasks, decomposition might be better. For some tasks, chain of thought is good. But it's a mathematical data set, so structured program seems to work better than other ones. So then the obvious thing would be if we are distilling these models, so how about we combine all the data that we have generated and then we just distill the model. So we did this, we call this combination. So all the correct samples which are generated by the LLMs. So we just distill this into this small model. And surprisingly, we didn't see any gains. Like in some cases, it was slightly worse than one of the strategies. And the reason for this is the model sometimes gets confused on which strategy to choose. If all of them are correct, and we are showing same problem but three different ways of solving it. So ideally, we want our models to learn this, but we did not see this as a beneficial strategy. So unless we give some signals to the model why it should prefer one of them, we didn't see any gains. So these are all the things on one side, so all the strategies. And on the other side, I'm also plotting the teacher results and just saying that there is still some performance gap that we want to fill. All the scaling helped a lot, but then how we can improve this further. So we go back to our second problem here. So we are saying there is a distributional mismatch between the language model and smaller language model. And this would be interesting to see how we can solve this. So how do we measure there is a distributional mismatch? So we have all the output sequences which we are using to train the smaller language model, and this is coming from the LLM. So all the output sequences that the small language model is seeing during its training, and then we ask the student model to generate this, and then we can see that there might be a mismatch between the two. And in like one way to solve this would be through self-training. So what I mean by this is there is a paper called GKD. So this paper says that if you take the student model and train it on its own self-generated data, then this would be beneficial for the students because it can lead to a reduction in this distribution mismatch. And the reason why this helps is because students are not like sometimes the student model is like really small and it's not expressive enough to fit the teacher's distribution. So so before I show that figure, so if it logically makes sense because if we can feed those student um, output to train itself, then we are kind of solidifying what the student model knows. And using your own data can also reduce the overall decay divergence between the teacher and the student data because we are mixing more and more student data now. So I'll come to this point, but like if we look this from another angle, why this approach would make sense. So this is another figure from uh, one of our paper where we are kind of trying to show that if you take three different size models, so we are here taking the smallest one being Llama Mistral 7 billion. The blue one is Llama 70 billion, and this purple one is GPT-4. We don't know the exact size, but let's assume this is the largest of them all. For a given task, we are sampling a lot of strategies. So for basically, we feed a question and then we sample multiple outputs for each of the model. And then we try to measure whether the answer or one of the answer, so whether one of the sample is correct or not, or whether answer exists in one of the output samples. And if we see this, like the green one, the Mistral smallest model, even when we are sampling it for 35 samples, we see that its accuracy goes from 40 to 90. And for GPT-4, it stays very consistent. So this is somehow showing that this smaller model knows how to solve a given task, but it is not picking its right strategy or right chain in its first attempt. But if you do some form of like an exhaustive search during inference, and if you have, let's say, a way to pick the right answer, so then it is possible to pick the right answer almost equally well compared to a larger model like Llama 70 billion or even GPT-4. So What we are saying here is if the smaller model knows how to solve a task, there should be a way to solidify this knowledge or make the model more confident towards choosing the right chain or choosing the right way to answer a given problem. And this we are saying that if you train on some self-generated samples, so this can assist in solidifying that knowledge. So there is a paper that also says something similar. So this paper says that if you train your um, model, some LLM, on some new information, and this new information can also mean something that the model has not seen during its pre-training or post-training stage. So then on this new information, model tends to hallucinate more. But if you train this model on something that it has seen before, then this would somehow solidify the knowledge in the model, and the chance of hallucination would go down. So combining all of these ideas, we can like create an approach where the model can learn two different things. So first, model can learn which strategy is suitable for a given task. So we have seen this before that sometimes one strategy is better than the other. So we can leverage this to teach model which strategy to choose, because we have seen in the combined results in the past, the model cannot do this implicitly. So it would be amazing if we can teach this to the model. And then we can also um, uh, take this self-training into account and solidify what the model knows. So based on all these ideas that I discussed before, we present one of our works. So this is called self-guided iterative knowledge distillation. So in a nutshell, what we are doing is we are starting the distillation training, as I mentioned before. So we use this LLM on the left to generate a lot of different reasoning strategies for a given input problem. And we are limiting ourselves to the three that I discussed before. So given a problem, we generate all these three kinds of strategies, and then combining all input and strategy pairs, we feed all this back to an SLM. So basically we are training like a smaller model with all the data which is generated from the larger model. So basically distillation, what we discussed before. Now, once we have trained the smaller model, so we feed this input problem again. So this is from the training data. And we ask the small language model to generate a lot of output sequences given a strategy. So here we are fixing chain of thought. So we are generating like n chain of thought reasoning chain for a given problem from the training data. And then we give this a hard reward. So here we are doing the ORM style reward. So we are looking at the final answer, and we are not doing PRM. So we don't care about the intermediate steps. So we look into the final outputs. We have access to ground truth, or we have access to LLM generated data, which we assume is correct. So either way, we can figure out which of the small language models generation matches with the larger models generation. And note here I'm saying about hard rewards, but of course we can also use soft rewards. So a couple of experiments we can do here is either training a reward model that can rank all of this and give rewards. We also tested with this self-consistency with a threshold. So we let the smaller model generate n outputs. We do a self-consistency or majority voting there. And then we put a threshold that if like over 0.5 or 0.6, if the model 6 out of 10 samples, for example, agree on one solution, so we say that this is correct, all the other ones are wrong, and so on. So we can make our decision. We found out that hard reward seems to work the best. So we are generating all these samples, giving rewards. And then we are creating a mixture of LLM data and SLM data now. So for all the samples where the small model would get something correct, so we take those samples from there. And then we also, for all the samples where none of the outputs are correct from any of the strategies, so we go to large language model's output and we take all the generated data from LLMs there. So we are creating some form of data mixing. And if we look at from a different angle, what essentially we are saying is if the model knows something, so you kind of exploit that information. So you solidify that knowledge and push the model towards that. But for those cases where the model does not know how to solve this, so you go to LLM and basically you're trying to explore there. So some form of exploitation we are doing for creating this data mixture, I would say. And then I will train the small language model here again. And this process is iterative. So we will train the small language model, then we generate multiple samples, give it a reward, make our data mix, train this again, and we do this iteratively. This is like some form of like on policy training. So we generate and train the last checkpoint that we are using. And this seems to work during training. During testing, we don't have to do anything. We just feed the input query to our small language model, so the model that we have trained. And we first predict the strategy that we are going to use. So in this case, starts with, let's say, chain of thought, and then it just decodes with the predicted strategy. So it's an autoregressive decoding during test time. So during inference, we're not doing any trick. One thing I wanted to mention here is whenever we are training this model, so there is also a token attached before the reasoning strategies, which also specifies which reasoning strategy we are using. So this gives the model some kind of knowledge that what strategy is suitable for a given task. And for example, if when we are generating this data, if the model can generate something correct with chain of thought, but it is not generating with other strategies, and then while in the data mix only says COT, so then the model kind of gets some implicit signal that for this specific kind of data, I should use this strategy, which is missing if you just do a combined data. So then everything is there. So this way, the model also learns to pick the right strategy during distillation. And like I was talking about reducing the KL divergence between the LLM and SLM data. And we can see this approach does that. So what we should look into is this green bar here. So green bar is the third one. So if you keep looking, this green bar goes in the middle of blue and orange bar. So blue is the teacher's data and orange is the student data. So over time, if you see this green bar kind of goes in between the blue and orange for all different strategies. So this is in some way saying that the alpha, if it goes down, so alpha 1 means all the data comes from the teacher, and lower the alpha, you can see more and more student data is being getting mixed in the training samples. So if you see overall the KL divergence goes down because we are now the training data has a lot of mix between LLM and SLM data. So eventually the overall divergence is low for such cases. So this approach also addresses the limitation of smaller model, which tends to consistently favor or pick one strategy all the time. So this is a plot which is like by vanilla distillation. By vanilla distillation, I mean you just generate all the data from large language model, feed this to smaller model, and then let the small model generate some or pick some strategy and solve it. So you see, larger models are equally capable to solve a given problem using all kinds of strategies, but the smaller models would end up picking like chain of thought, for example, all the time. And the reason, like a lot of this has to do with the pre-training biases for smaller models, and it has seen a lot of chain of thought strategy during it. But this is not the case in our case. So it's a slightly different figure, but it is saying the same thing. So if we look on the left side, so I'm giving this iteration 0. So iteration 0 means like all the outputs are generated after a combined distillation. So no, like our approach has not been applied yet. So combined distillation, you see for two of the strategies. So L2M and CO2 in this case is 0, and model always picks this green strategy. So in this case, program of thought. But more and more training we are doing. So every iteration is one generation, selection, creating the data set and training. So you see, eventually the model is picking like other strategies in orange and blue. And then this, like this green one is going down. So the model also tends to pick some other strategies. Or on the right side, if we look at the accuracy score of the same. So the green one, even though it is reducing so the number of samples that it is picking, if the accuracy is not going down, in fact, it goes up over iteration. And then the blue and orange, which was 0 before here, now you see there is a gradually some accurate samples. So in other way, it is saying that the model tends to pick other strategies when it is not confident with one of them, and kind of it is trying to pick those samples where the accuracy, where the model thinks that it is not very sure, and in some way it is not leaving its correct samples for other strategies. Rather, it is picking for incorrect solutions where it is getting with the green strategy. It is trying to pick the blue and orange. So overall, all of the three strategies scores goes up. And one other important thing with our approach is if you take this strategy. So, like when I was mentioning, you let the model, our student model, generate the all kinds of solutions with all three different strategies. So you can also make the model biased. So for example, when this smaller language model is generating with chain of thought, let's say we have a couple of samples correct and we just pick one of them. Then there is also program of thought for the same input sample. We got something correct. For L2M, let's say we also got something correct. Now you want to have a solution where you care about programming, let's say more. So in that case, you will ignore the chain of thought and L2M. And for all the cases where program of thought is correct and other strategies are correct, you always pick program of thought and you discard the other samples. And only pick other strategies when program of thought is not right. So this way you are kind of biasing your model to always pick program of thought and only pick other strategies when it is not confident with program of thought. And this bias you can create with any of the strategies which you have. And when you put all three strategies, whichever ones are correct, so we call this uniform distillation, and we call it bias distillation when we pick a bias strategy. So we are trying to force the model to become biased towards one of the strategies. So we compare our bias strategies with non-biased strategies. So non-biased are normal lines and bias strategies with the slanted line. And we see for all different data sets, for all different strategies, our bias models outperform the normal one. And yeah, so this is somehow saying that for all the samples where the model is confident with the given strategy, it picks that, but it also tries to pick some other strategies when it is not. So in a way, we are showing that selection of strategies also makes sense. And this is the same result from before. So these are all the three strategies, and now the red is our approach. So the SIKeD model gets like a couple of points boost over normal distillation. So this was the goal.
Uh,
And
Kumar, a
yeah,
question here. Um,
yes.
how do you think the relative size of the teacher model impacts these results? And do you need the model to be at least, say, X times bigger than the student model for something like this to work?
Mhm.
Or could the teacher model
Mm.
also be like too big?
In our case, we figured out that more than size, the expertness of the model matters more. So if Llama 70 billion, so comparing Llama 70 billion and Llama 8 billion, we use both of them as teachers. So Llama 8 billion accuracy was lower than Llama 70 billion. So when we trained our student models, we observed that Llama 70 billion was preferred by the students. Um, and when we went to GPT-4, then the performance went up. So the more expert the teacher, the better it can train the student models. So on a very side, like orthogonal experiments, we also tried this where we have Llama 70 billion, then we distill 8 billion, then we distill 1 billion. No, not 1, 3 billion. Versus distilling this 3 billion directly from Llama 70 billion. And we observed that directly distillation saves some compute, so because we are not doing 2 times, and the results are like kind of similar or slightly better with um, directly distilling from a larger model.
So either for your iterative process or even for distillation in general, would you recommend distilling from the largest possible model always?
I would say so. At
Okay.
least that's what we observe.
Okay.
The larger the model, better the performance. Um, yes. So yeah, so this performance with our approach goes up. And then one final thing to also say about alpha value. So the alpha of 1 means we are just using the teacher and distilling everything. And alpha 0 means we are generating all the data from the smaller models and self-training. And we are showing that an alpha value of in between, so having a mixture of teacher and student works best. And yeah, this is shown by like 3 different alpha values over iteration that we got. And this seems to work better. So we just compare ourselves with the 2 extreme cases. And then we basically, in this work, we showed that self-training can be used to improve the reasoning capabilities. But then the question is, should it be limited to just distillation? Or in other words, when we are distilling this reasoning from a larger model to smaller models, so when a model is predicting an incorrect strategy in our case, so we just ignore that sample. But we are not giving this sample back to the model or some signal back to the model saying that you made a mistake with chain of thought, so you are picking program of thought. The some implicit knowledge is there because the model is not seeing a chain of thought sample, but seeing a program of thought sample. So this is giving some implicit knowledge to the model that for this task, I should pick program of thought. But there is no external, um, there is no external signal that we are giving to the model that it makes sense to pick this strategy over the other. So some signal that one strategy is correct and one strategy is incorrect would be great. So we extended our last work to create some kind of self-learning meta strategy for reasoning. And this works as following. So we have a question, we give it to the model, and we generate uh, some strategy, and we generate some solution for this. If everything is correct, we say, okay, this is nice. But we are also saying that for this given question, if the model is generating something which is incorrect, then in this case, we should do a refinement. And during this refinement, if we give this incorrect sample or incorrect strategy information to the model. So now the model can condition on the question and then the incorrect strategy that it selected, and then make a more informed decision that maybe I picked this strategy, I got this incorrect, so maybe I should pick a different strategy. So in this way, we are giving some form of explicitly, we are showing the model that you picked this and this might be incorrect. And then we can run this simulation for as long as we want till we reach to a final answer. And then our goal would be to show this correct, all kinds of correct strategies to the model. So we collect all these reasoning chains, and then we train our language model like iteratively. So if we go into the process, like in short, given a problem, model will pick a strategy and generate a reasoning chain. If it is correct, then we say, okay, this is good. We give it a reward of 1 and we move on. We take another sample and say, let's say this time the model picked some strategy and this is incorrect. So then this calls for a refinement. So now we give this extra signal to the model saying this is your incorrect strategy that you have selected. Then you have an input problem now. And can you find out like maybe a different strategy or different way of solving this? And then we give an extra tag that model is like kind of forced or is trying to pick a correct strategy. And let's say model picks something else. If it is correct, then let's say it's not correct, then we give this incorrect strategy back to the model and we run the simulation for as long as we want. Once we are done with all the simulations, so either we get the correct strategy and correct trajectory, or let's say we reached the maximum number of simulations that we want to run, then we collect all the correct trajectories directly, and we all the this like the long trajectory that we unroll, so we trim away everything and we take the final reasoning chain and the strategy associated with it, and then we create this training data again. So the difference from our last approach and this approach is, in this case we are running like a big simulation during training, but during testing we just want the search to be linear. So we can run as big simulations as we want during training, collect all the input and correct reasoning strategy and reasoning chain, and then we feed this to LLM and train our model. And then this would be done iteratively. So there is no larger model involved here. So the model will come itself, start decoding, start running all the strategies, collect all the sample, train itself, and then repeat the process again. And there is a huge performance improvement if we check here. So I'm showing Gemma and Mistral here. There are some other models in the paper, but if you take a Gemma model or Mistral model out of the box and ask it to solve a problem using one of the given strategies, so the accuracy that we get is around 40s or 50s. So 40 for Gemma and approximately 50 to 55 for Mistral. And if you use this iterative strategy that we say, that we propose, so our results goes from 40 to 55 for Gemma. And from Mistral, it goes from 55-ish to almost late 60s, so 68 or something. So we get huge performance boost. And note that this can also be used for refinement. So we compare ourselves with approaches like self-refine, where with an Oracle verifier, we let the model first pick a strategy. So let's say model is 40% accurate. For the rest, 60% of the samples, we ask the model to refine itself. And now the accuracy goes from 40 to 45, and this goes from 50 to 60. And we do the same with our approach. So we let the model first predict the output in choosing a given strategy, whatever the model selects. And then we, through an Oracle verifier, we say this is correct or incorrect. For all the incorrect samples, we resample again. And now our accuracy goes comparatively from 45 to 68. And here we go from 60 to almost 80. So we get plus 15 to 20 points boost. Yeah, which is like a lot. And finally, we also check if our approach works. So can we combine our work of distillation and our work of iterative refinement? So we take this 40% JEMA model and we train it with large language models output. So we do distillation and then we run a couple of iteration of uh, like the second approach, like self refinement approach. And we see that there is some improvements that we are seeing consistently. Yeah, so these were all the approaches of self-training that we leveraged in distillation and in refinement. And going forward, I think all the things that I have tested is like post-training in many ways. But what if we can leverage this on pre-training? So this could be one of the interesting things. We are also exploring, and I think in future might be very interesting to check. So, for example, when we are doing a pre-training, so we will, let's say, start by pre-training on X tokens. And this is really important for the models to learn um, some association between words and how to make correct sentences and some meaningful sentences. But obviously, when we do pre-training, so we pre-train up to X tokens, and then we start doing some post-training. We also want to increase the context length of the models, and we also do lots of preference optimization and so on. So this really helps the model to understand a lot of tasks. Especially instruction tuning is very important. So let's say instead of doing this pre-training on all the tokens, we do pre-training on X tokens, and then we do some form of instruction tuning on a small subset of downstream tasks. This instruction tuning would be important because for self-training, we want to generate data, and to generate data, we want the models to follow some kind of instruction. So let's say we pre-train on some smaller number of total tokens that we have, and we do an instruction tuning. Then we generate the model's output from this current checkpoint that we have. And with some um, like constraints, we check whether these data samples are of high quality or not. And this can easily be tested given on a lot of like tasks that we are defining. So all kinds of instruction tuning tasks and a variety of downstream tasks. We can easily verify if the data is of high quality or not. So what we can do is we take these high quality generated data, they combine this with the pre-training data on like a lot of other tokens that is left, and then we train the models further. And then this process can also be repeated. So currently, instead of doing this for one time, we can also repeat this process by pre-training for some time, doing small instruction tuning, generating lots of data, adding this high quality data back, and then continue the pre-training chain. And one reason why I'm saying this might be interesting is eventually we might need lower or lesser total number of tokens to pre-train the model, and we can still achieve good results because pre-training would allow the exploration and then self-generated data would do the exploitation and some solidifying of knowledge, whatever the model is learning, and we can repeat this. And something like DeepSeek R1 lately has shown that multiple rounds of fine-tuning RL helps. And we also like generated data from some last checkpoints, use that in their whole process, like from a reference model, they generated data and use in their checkpoints, and that also seems to be helpful. So one idea to explore could be how we can leverage the self-training during pre-training stage. And we can test this on smaller models and then see if it works there, and then we can always think about scaling. But yeah, nonetheless, we can explore this in future. And this was my last slide. So before I go, I'm just summarizing everything that we discussed just now. So I talked about how self-training can assist smaller models in learning better from a large language model and can prove helpful in reducing their distributional mismatch. And it can also allow models to refine their answer or can learn um, a given optimal strategy, or not optimal, but a better strategy for solving a given task in its first attempt. And in future can also be applied during pre-training, but this is something I'm still testing, so I cannot say for sure. Thank you so much for joining, and yeah, it was a pleasure presenting the paper. Thank you so much. And happy to answer any questions if you have.
I have a great talk. Thank you. I have a question. So in your second work, I forgot the name.
Smart, we call it smart, but
Yeah.
yeah.
So in this work, you are, as far as I'm understanding, you are generating trajectories. If the model agrees that, like, if they are correct, you mix it with your data and then reintroduce it in the supervised fine-tuning stage, right?
Yes, that's
So
correct.
in a sense, how do you compare it with current, most recent reinforcement learning based approaches?
That's very interesting. So the first project that we did in 2021, uh, we compared ourselves to our project that we did there, and that is kind of in 21. It was very similar to the R1 that we have now. So in our project, we said that you have a planner model that would plan something. So we do some planning, and then we did all generations of different trajectories. We check which ones are correct, which ones are incorrect, and we give rewards based on from a model, and also some rule-based rewards. So we felt that whether our reasoning trajectories are going in the right direction, right set of decomposition is done, and so on. And then we subtracted a baseline, which was an average over all the generations that we had, because at the time we didn't have compute. So we thought this is a nice strategy. And then we trained ourselves with reinforce. So this is what we did back then. And we compare ourselves with that strategy, and we feel this could be seen as an approximation of that.
Mm-hmm.
And there is another paper or another direction of paper called REST, which is called reinforced self-training or something. This REST paper also says that if you generate multiple tokens or multiple generations, and then you pick out some samples, which ones are good over a threshold or not, and use that threshold, like keep moving that threshold up and up and up over iterations, and you pick like really good quality samples and train your model. So this is also an approximation of RLHF. And this is in a way saying that you are kind of giving this like some kind of preference to the model. In a way, it is picking the right one and rejecting the wrong ones. In our case, also with this correct token that we are putting everywhere. So this correct token is also somewhere like asking the model to pick a given strategy which it thinks is correct. And then in training data, we show only the correct ones. So it it is a way going in the same direction. We did not compare ourselves with GRPO, which would be interesting. But then GRPO came after our paper, so we did not do that. But it would be interesting to see. But definitely, it should be comparable to the RLHF, like PPO style approaches, at least, or yeah, like at least the REST paper claims that It is similar, and one of the authors of our paper is the lead author of REST. So we also verified, obviously he's part of this paper, so he verified that this makes sense. So it should be in that direction, I would say.
Thank you.
Yeah. If there are any more questions, happy to answer.
Looks like we're all good on questions. So let's go ahead and give Kumar a big thanks on sharing his presentation today.
Thank you so
And then
much.
Kumar, enjoy the rest of your conversations with the team today.